Okay, so how is everyone today? Good, I hope. Okay, so last time we were talking about function composition, and we're still talking about that. Specifically, last time we talked about adding and multiplying, and we said something like if you can take two numbers and you can add them to get another number, and you can do this thing called add. Another thing you can do is you can take two numbers and you can multiply them to get another number. And finally, we said if you take two functions, now instead of taking two numbers, you take two functions, you can compose them and get a new function. So generally speaking, this pattern of taking two things of the same kind, combining them, and getting another thing of the same kind, this happens all the time in math, and human beings are quite good at it, conceptually anyway. For example, I think it would be totally unsurprising if I said, hey, I combined two cats and got another cat, right? That's totally normal. That's totally expected. Okay. So specifically, we can take two functions. So given two functions, f and g, we can combine them with, so now, the first time we said it was given two numbers, we can combine them with, and then I wrote some punctuation. The first time the punctuation was plus. We can combine them with plus, right? And then the second time we said oh, and also we can combine two numbers with multiply, which we denoted with a dot. The punctuation for the combination that we're talking about with functions is an open circle. We can combine them with open circle. This is pronounced out loud as compose, or circ, as in the first four letters of the word circle. We can combine them with compose to get another function. Another function, f composed with g. The definition of this function is f composed with g evaluated at x is f of g of x So now, to be clear about this, what this is one of the ideas, one of the conceptual devices that we're going to use to help us understand this is the notion of an assembly line. So what's happening here, I'd like for you to imagine that we have an X, and then it goes down a conveyor belt to the G machine. So it goes to the G machine, and then out comes G of X. Out comes a G of X, and then this output G of X proceeds further on the conveyor belt to the F machine, and out comes what? F of G of X. So what I want you to observe is that f of g of x is like setting up an assembly line with two machines in a row. The input proceeds through the G machine first, and then creates its output, and then that output is used as input to the F machine, etc. That being said, there's nothing sacred about doing it in that order. If we wanted the machines to be in the other order, then what would we write? G circ F. So G circ F evaluated at x Okay, now how do we write this without the composition operator? G of f of x. Notice that in this notation, the x goes to whichever function it is closest to. So in this notation, x is going to visit f first, and then g second. Making the assembly line picture, this is x proceeds to the f machine first. Out comes f of x. The result continues down the conveyor belt to the g machine, and out comes g of f of x. Okay. One thing I want to mention is that I'm aware that in high school, when this is talked about, it is very common for instructors to refer to this as fog, but I will never say that again because I find it, well, honestly, from a teaching point of view, I find it a little bit offensive because, well, there's such a thing as a false friend in knowledge. That is to say, you making a false connection to something. So I'm never going to pronounce this as fog or goff, but if you look at your book, it might say that. I don't know. Good. So F composed with G, G composed with F. Good. It's not that I'll take off if I hear you saying fog in the hallway or something like that. I'm just not going to do that. Okay. Good. So now, with the assembly line analogy, I want to make sure that you understand something about this. We've talked about adding numbers. We've talked about multiplying numbers. Now, adding and multiplying, they have the nice property that they commute, which is to say that, for example, 13 plus 14 is the same as 14 plus 13. It's the same, doesn't matter. Similarly, 13 multiplied by 14 is the same as 14 multiplied by 13 because multiplication commutes. And so, every once in a while, with my kids, you know, they want peanut butter and jelly sandwiches for lunch every day. So every once in a while they're eating breakfast, I tell them, well, I mixed it up, and I decided not to make you peanut butter and jelly sandwiches today. Instead, I made you jelly and peanut butter sandwiches. To which my 6-year-old will say, Dada, you know that peanut butter and jelly commute in sandwiches. Right? Of course. So, but composition doesn't commute. It doesn't commute, and I want you to know that that's a totally natural thing, that it doesn't commute. So imagine that we work in a doll manufacturing business, and that we've got a machine that the dolls pass through that puts on left shoes, and another machine that they pass through that puts on right shoes. Now, as far as the finished product is concerned, it doesn't matter what order those machines are in, because if you're just looking at the finished product, you wouldn't be able to tell whether or not the doll passed through the left shoe, put her on her first, or the right shoe, put her on her first. You wouldn't be able to tell. But if we had a put on the pants machine and a put on the underwear machine, you'd be able to tell, right? Because in one order, it's like a Ken doll, you know, Barbie's counterpart, Ken, and the other one is like a Superman doll. It's very different. So the order of the machines generally is going to matter. So let's see that it will matter. For example, so we could say let f of x be 13x plus 14, and let g of x be, I don't know, 4 times x squared plus 3x plus 5. So we've got two functions, And what we're going to do is we're going to compose these functions in both orders and simplify, and we're going to on the one hand, practice doing that just as a thing unto itself, but we're also going to witness that the results are different. So first, f composed with g evaluated at x. Well, how do we write this without the composition operator?
You have to put the g of x and the parentheses with it. No, the f and then parentheses g of x, right?
Very good. So f of g of x, which is to say that x is given to g first. Okay, so now to get this right, I'm going to use a bit of psychological trickery. So human beings with our visual systems are quite good at matching. So what I'm going to do is I'm going to cover this up because I find that covering that up keeps a false match from triggering in you. So whatever we give f, what it's going to do is it's going to multiply it by 13 and then add 14. That's what it's going to do. So if we gave it a 10, it would do multiply by 13, add 14. If we gave it a banana, it'd multiply by 13, add 14. Well, so that means that everywhere we see an x, I'm going to write an empty pair of parentheses, just a slot where something can be put in. So 13, slot, add 14. Okay, and then whatever it is that I'm covering up, that's what needs to be written in there, right? If it's an 8, write an 8. If it's a giraffe, write a giraffe. So what is in there? A g of x. So I'll write g of x. Okay. So now we're done with what f does. So now this red, we can replace it with what? Right, all that stuff. Okay, so 13 multiplied by 4x squared plus 3x plus 5 plus 14. So now all substitutions are complete, and now it's just a matter of carrying out the algebraic steps. So I'll distribute the 13 and get 52 x squared plus 39x plus 65 plus 14. That 14 was already there. And then now I'll collect 52x squared plus 39x plus 79. Good. Any question about this one?
Are we done?
No, we're going to do it in the other order now. But we're finished with this one. Now, if composition commuted, if it did commute, then we should expect that g composed with f evaluated at x should be exactly this, if it commuted. But it doesn't. So that doesn't mean that if you do the composition in the other order, you'll never get the same thing. That's not true. What I am saying is that you should have no expectation of getting the same thing. Okay. So g composed with f evaluated at x. How do we write that without the composition operator? G of f of x. And so again, I'm going to cover up this f to try and keep you from your pattern matching facility from being overloaded. So notice what g does. Whatever you give g, it uses it in two places. It uses it once for this term, because there's an x there, and it uses it a second time for this term. So every place that we see an X, we're going to write a slot, a big pair of open parentheses into which we can put something. So it'll look like 4 times slot squared plus 3 times slot, add 5. So that's what it looks like. Because in G's formula, we used X twice, and those are the places that we used them. So whatever I uncover, that's what we need to write in there. If we uncover a burrito, then well, that's what we'll have to write in there. What's actually written there is an f of x, so that's what we write in there. Any question about that? So now we make that substitution. So that'd be 4, and then what's written in here is 13x. What needs to be written is 13x plus 14 squared, and then plus 3 multiplied by 13x plus 14, and then add 5. Now it's all over except for the algebra. All right. So that one's easy enough. This one can be done with just a little bit, right? You got to distribute. So I won't ask about those, but I do want to ask about this one. What needs to occur first? The squaring, right? The squaring, because there's, in a sense, a competition between what the 4 wants to do and what the 2 wants to do. The 4 wants to participate in what operation?
Multiplication.
A multiply. And the 2?
Parentheses?
An exponent.
Okay, so it's not parentheses technically, it's exponent, both of which come before multiplication, but we're focused on.
Right. Well, I'll say it like this. Inside of those parentheses, because they're inside of parentheses, if there were any simplifications to do, you should do those.
Yeah.
But because having a look at what's in those parentheses, there's no simplification to do. So in a sense, it's already done. So then the next question is that concerning the contents of those parentheses, I see the 4 wants to get in on the action, and so does the 2. But the 2 is saying I want to be an exponent, and this 4 is saying I want to be a multiplier. So the order of operation says the square occurs first. Okay, so then you can either remember the formula for the square of a binomial, a plus b all squared, or you can FOIL it out in your head, whatever you like. I'll FOIL it. So the f term, that would be 13x times 13x. That's 169x squared. The O term would be 13x multiplied by 14, which is 169 plus another 13, which would be
190. Oh, it's 784.
No. 182. Yeah, 182. So that'd be plus 182 x's for the O term. For the I term, another 182. Because remember, in FOIL, there's, 4 terms, right? F, O, I, and L. So that's...
It's 183.
Is it 3? No, it's 2. It'd have to be 2, right? Because it's the product of 13 and 14 has to be even. Right? I know that 13 squared is 169. And then if you add another 13, that's 182.
Okay.
Then now 14 squared, that's 196. Good. So that's the square, right? That's just 4 and then the square. So now we've got to not forget these, right? So then that'd be 39 x's plus what? Did I make an error?
182 2 times.
Yeah. Because there's an O and an I, right? This one times that one is O. That one times that one is I. Alternatively, you've got to remember in the a plus b all squared, it's a squared plus twice ab plus b squared. Okay, so then 39x plus 42 plus 5. Okay, good. Now that the exponent is out of the way, now the 4 is free to participate. Now I'm getting beyond my depth here, my arithmetic depth. Okay. 4 times 169, 676 x squared, and then plus 182 plus 182, and then multiply that by 4, 1,456. Really? Yeah. X's. Okay. And then 4 times 196, 784. And then these are just along for the ride. Well, 42 and 5 is 47. And now a little more collect. I see that we have 676 x squareds. And then collecting the x's, here I see we have 1,456 of them and another 39. So 1495. Concerning the units, I see 784 plus 47. 831. Okay. Any question about this one? So now, I'd like for you to observe that these are not the same, right? And I, again, want to insist that this is the most natural thing possible, right? This one is the Ken doll. This one is the Superman doll. Okay. Any question about this? Okay. So, last time, I asked a question like this. Or at least we have enough information for me to ask a question like this. What is the additive inverse of -3? -3. Okay, I agree, and I'm just going to write 3 because I think we all understand that. But here's a, yes? Uh-huh.
Is it important for us to, when we get the final answer, to write it as f of g of x equals whatever the answer is?
I think, if I understand your question, I think you're asking, should you copy this again and write it on the left-hand side? That would be fine, but as long as it's clear. See, I would claim that, for example, if I hadn't written this vertical line, it'd be kind of unclear what I meant, because you could construe that as meaning, well, does this one extend to that one? So just as long as it's clear. So yes, I agree. The additive inverse of -3 is 3. And most students can respond with the correct answer without hesitation. Then here's where the hesitation comes. Y is 3. Y is 3. The additive inverse of -3.
Because 0 is the additive identity.
Okay.
And negative 3, or 3, allows you to arrive at the additive
Okay, you're right on top of it, but you're missing one key bit.
If you combine -3 and 3
Mm-hmm.
with addition, you get the additive identity.
Exactly that. So the reason why you were just that much off is because you said more or less something like, if you combine them, then you get 0. But it wasn't clear to me that you knew that you meant combining with addition.
Yeah.
So the reason why is because when you add 3 and -3, you get the additive identity, which is to say 3 plus -3 is 0. And 0 is significant because it's the additive identity. The additive identity. And the additive identity is 0, and it has the property that x plus 0 is x for all x. Now, again, to make another kind of analogy, like a word processor analogy, you've got an undo button. This question kind of can be said like, well, what's the undo button for adding -3? The undo button is adding +3, right? If you if you do something and the thing that you did was add -3, then the undo button will add +3, because that's the same as doing nothing. The undo button for adding 7 is adding -7. But 0 is the identity because adding 0 doesn't need an undo button because it didn't do anything. So it's the identity. Similarly, what is the multiplicative inverse of -2/3? -3/2. Okay, and usually students can respond with the correct answer, and this is the correct answer, more or less rapidly. But it is usually more difficult for them to respond to the question of why is -3/2 the multiplicative inverse of -2/3. So why?
Is it hard or simple? Example something to look at.
Well, so given a number, if it has a multiplicative inverse, its multiplicative inverse is reciprocal, which I suspect is how you came up with it. But then the question is okay, supposing you did that, why is it that these two are multiplicative inverses? Yes?
If you combine them by multiplying them together, you get 1, and 1 is the multiplicative identity.
Exactly this.
Multiplying by 1 is the same as
That's right.
She said combine, and I was like, uh-oh, that's trouble. And then she said combine by multiplying. I was like,
All right. Because when you multiply -3/2 and -2/3, you get the multiplicative identity. Specifically, -3/2 multiplied by -2/3 is, well, the negatives will cancel, the 3's will cancel, the 2's will cancel, and you're left with 1. And the reason why 1 is important is because this is the multiplicative identity. It is the multiplicative identity because x multiplied by 1 is x for all x. Yeah, right. No, it is in fact right, because 0 multiplied by 1 is 0. But I do agree with what you probably meant, that 0 doesn't have an inverse, a multiplicative inverse. Yes?
On the exam, will you want us to identify multiplicative identity?
No, not really, because the only reason why I'm saying this is to build up the conceptual framework for what I'm about to say.
Okay, I just wanted to know if it was like fair game.
Right, yeah, I'm not going to really ask that. I lost my train of thought. What is it? Blah, 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 get the blah, 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 blah. So again, to make the word processor analogy, what is the undo button for multiplying by 7? Divide by 7, or if you like, multiply by 1/7. The undo button for multiplying by 13 over 14 is multiplying by 14 over 13, because that undoes it. However, additionally, multiplication by 1, you don't need an undo button, because it didn't do anything. That's why 1 is the identity. So now, this structure occurs all over the place in the world, and especially in math, where we have a way to take two things of the same kind, combine them to make a third thing of the same kind. We want something that's the identity, which is to say that a combination with this is the same as doing nothing. And in order to make sense of it all, we need an identity, and we're going to have inverses and things like that. So, as a result of this discussion, what I'm telling you is that now the punctuation that we're going to start talking about is not add, it is not multiply. The punctuation we're going to talk about is compose. And to be able to to be able to talk about this, therefore, to talk about compose, we need the compositional identity. We're going to need to have it. Once we have it, we'll be able to tell, we can tell, when functions are compositional inverses. Because, well, how about are 5 and -8 additive inverses? Why not?
When you add them, you don't combine
Combined with addition, they do not equal the additive identity.
Exactly that. When you combine them with addition, 5 and -8, you get -3. Is -3 the additive identity? It is not, and therefore these two are not additive inverses. As a result, whenever we figure out on the next page what the compositional identity is, we can tell when two functions are compositional inverses when we compose them and get that compositional identity. Okay, so we need to figure out what it is. Well, here it is. The compositional identity is denoted. So just like we can write 0 and that means what it means, and we can write 1 and that means what it means, the compositional identity is denoted ID. And remember I write the math stuff in script. So ID, and it is defined ID of x is x. So what I mean is that ID is a function, a machine. You line up the x on the conveyor belt, you give it to the ID machine, and out comes an x. That's what comes out. This is as opposed to, say, this function right here, when you give it when you give it an x as input, 13x plus 14 comes out. What I'm saying is that this is a machine where you give it an x and out comes an x. If 5 is input, 5 is output. If a banana is input, a banana is output. Okay. Now the reason why this is the identity is because of the following. So observe. For example, f composed with ID. So f composed with ID evaluated at x. Now how can we write this without the composition operation? F of ID of x, right? Just like f of g of x on the previous page. And then what's the formula for ID of x? X. So what I want you to see is that what effect did that ID have? None, right? So as a result, we know that f composed with ID is f. So giving x to ID first is the same as having not done that. So okay. What if we do it in the other order? What if we do ID composed with f? Okay. ID composed with f, evaluate at x. Well, how can we write this without the composition operator? ID of f of x. And now, again, this is where the human pattern matching is both strong and weak. Whatever it is that I'm covering up, that's what's going to come back out, because that's what ID does. If you give it a giraffe as input, then that giraffe is the output. So whatever I'm covering up, that's what's coming out. So what's the output? F of x. Therefore, ID composed with f is f. So what I want you to see is that, well, the order of composition matters. However, composing f on the right with ID is the same as not doing that, and composing f on the left with ID is the same as not doing that. Now, I want to convince you that this is a totally natural kind of idea. So to make the assembly line, analogy. Well, suppose that again we're doing these dolls, I guess. The only thing that we need is that this is not a time-sensitive operation, right? Not something like a fruit, you know, something that can spoil, but something like a plastic doll. So we give the input to the f machine, and out comes f of x. And again, imagine that we're on a factory floor. What if these arrows represent spans of conveyor belt? And what if we take that conveyor belt that's maybe like, you know, like 2 meters, and then we make it like 10 meters long, so that that input actually has to travel down the conveyor belt for longer than before. What will come out? F of x, right? It makes that doesn't affect the situation. Okay. So what I'm saying is that the identity function is just a little stretch of conveyor belt. That's all that it is. Because if you give x, and instead of making a little stretch of conveyor belt, if you just insert an identity machine, well, the x goes into the identity machine, and what comes out? X does. And then it proceeds further to the f machine. Oops. And what comes out? f of x. So does making the conveyor belt before the machine change a little longer, making the conveyor belt longer, stretching it out, does it change the output? No. What if you stretch the conveyor belt that comes after the machine? Does that change the output? No. In the exact same way that stretching the conveyor belt before and after the machine doesn't affect the output, putting an identity machine before or after doesn't affect anything. Okay, good. So that's why ID is the identity function. Good. Any question about this? Okay. So now, so for example, show the following functions are compositional inverses. Okay, show their inverses. So here they are. F of x is 7 multiplied by x cubed plus 5, and g of x is the cube root of x minus 5 over 7. So, well, if I gave you two numbers and I said show that these are additive inverses, what would you do? Add them and demonstrate that you obtain the additive identity. If I gave you two numbers and said demonstrate that they are multiplicative inverses, then you would multiply them and show that you obtain the multiplicative identity. So I've given you two functions and I want you to demonstrate that they're compositional inverses. So what are you going to do? Compose them, right? Sometimes I feel like I'm like hammering the thing too hard, but I know what's going to happen next week. Probably for those people who aren't here, sadly. Okay, so then let's do it. F composed with G, evaluate at X. We want to, well, the first thing we need to do is write these in Gesundheit. We need to write these without composition. So that's F of G of X. Okay, and again with the slotting, pattern matching. F is what we're doing on the outside, so I'm going to take F's formula, and everywhere I see an X, I'm going to write a big parentheses slot. So then I can see X is used once, so I just need one slot. So it'll look like this. 7 multiplied by, and then there's that slot, which is going to be cubed, and then add 5. And then what goes in the slot? Right, I could write all that right now, but I find that it works better to provide an intermediate. Okay, so I did that, and now I'll replace g of x with what it does. So this will be 7 multiplied by okay. So now I want to sort of describe to you, this is the composed machine, right? We've got an F machine and a G machine, and this is what the composed machine does. So I want to sort of stress for you how what it's doing, kind of in a complicated way. It's saying, okay, this is what I'm going to do. I'm going to take the x, I'm going to subtract 5. After I've done that, I'm going to divide by 7 and then compute the cube root. And now I'm halfway done. Now that I'm halfway done, I'm going to cube that, multiply by 7, and then add 5. That's what I'm going to do. Okay. Pretty noisy. So what? The cube and the cube root cancel. Because ignoring what's happening here for a moment, you can see that whatever I'm covering up, we're going to compute the cube root of that, and then immediately following, we're going to cube that. So compute cube root and then cube that. That's the same as not doing anything. So this would be 7 multiplied by x minus 5 over 7. And then add 5. Now what? The 7s. Oh, the 7s cancel. Now what? Oh, the 5s cancel. Okay, so I want to sort of point out what's happening. We've got a machine that does this. We've got a machine that does that. And if we stitch them together in the order that X goes to the G machine first and then the F machine, this is the result. And you can imagine an X is going down the assembly line, right? And then it comes to this machine, and you can't really see what's happening, but all of a sudden you hear all kinds of hammering, and sawing, and cats crying, and all kinds of stuff, right? Like, and then a few moments later, the X comes out. Nothing at all happened to it. It's the same exact thing you put in. All right? Well, we need to do it in the other order. So G composed with F. That is to say, what if we put the machines, what if we line up the machines in the other order? Then what? Well, we'll just have to see. Again, with the slotting technique, so this would be 3 cube root, and then I can see that that's where a slot is, so slot, and then subtract 5, and then divide by 7. And then what is it that I need to write in that slot? F of x. So then this would be cube root of So this is the composed machine. What it's going to do is that whatever x you give it, it's going to first cube that x, then multiply that by 7, then add 5. And now that it's halfway done, it's going to subtract 5, divide all that by 7, and then compute cube root. Okay? So, looking at this algebraically, we can drop those parentheses and then what? Cancel the 5s. Now that the 5s are canceled, the 7s cancel. Okay, now what about this? The cube and the cube root cancel. Now wait a second, I'm starting to get a little bit anxious. I'm not sure. Do they cancel? Because I seem to remember something about them not always canceling. Okay, so here I'm asking about the cube root and the cube. If I was to go back in time and change that to an 8 and that to 8th root, then we would get here in the same place, and instead I'd be asking about the 8th root of x to 8. But as it happens, we're talking about the cube root of x to 3. And so, as you say, so which one is this? This is x. What about this one? This one is absolute value of x. And how do you, what is the signal that you're in this case or that case? Parity, right? So what I mean to say is that the answer here is x. And that means that, look at this complicated machine. You put the x in, and then all this crazy stuff happens, and then the exact same x comes right back out, right? It's just like the x has gone down a noisy conveyor belt. Taking these together, that means that we have demonstrated, we can say, therefore, f and g are compositional inverses. However, if you take this exercise and make it exactly the same, except changing from cube and cube root to fourth, to exponent 4 and fourth root, then they're not inverses. Because on this one, you will come to the absolute value of x, which means that in this order, those machines are not the identity. They're not a conveyor belt. They're a machine that does one little thing. If it happens to be positive, it is a conveyor belt, or 0. If it's negative, it flips it to be positive. So that's absolute value. Good. So here's the last thing that I want to leave us with, and that is it's the first thing we're going to talk about next time. And that is, okay, we've seen the compositional identity. We've seen how to confirm or deny whether or not two functions are compositional inverses. But here's a different question. For addition, which numbers have an additive inverse? All of them. For multiplication, which numbers have a multiplicative inverse? Everything except 0. Now the question is which functions have a compositional inverse? Because it's not all of them.
All functions except those with even radicals?
Well, some of those are not going to have, or will not, but some of them will. In the end, here's the last idea. If you have the parabola vending machine, that is to say, you press button 5 and out comes 5 squared, 25. If you witness someone obtain a 25, that's the output you witness. Do you know what button that they pressed for sure? No, because they could have pressed 5 or -5. So it's not possible to run that machine in reverse. Okay, so I'll leave us there. A machine that can't be reversed. Have a nice Monday. Hi.
Okay, quick question.
Okay.
So, I accidentally left my 301 at home. Is that a completion or is that an out of 10? Because I have all the other ones. The other one I just like slipped, I guess.
Well, in the end, I don't know because I haven't decided.
Okay.
I mean, what if you just want to know what happens is that I'm going to go back to my office. I'm going to get all the things ready, and then I'm going to more or less randomly say this one happened, that one.
Okay.
So in the end, I don't know the answer.
Okay.
But supposing the worst case scenario, that it is graded and that you're going to get a 0, well, you'll be able to do it on the final.
Thank you.